His report is centered around protecting the UK from the most serious respiratory infections of flu, TB, and COVID-19. His patient-based research aims to understand the body's natural mechanisms of protection against all of these lethal pathogens and the determinants of transmission as well. He translates his discoveries into innovative practical solutions to improve patient care and public health, which include anywhere from developing a blueprint for a universal pandemic flu vaccine to elucidating the mechanism of action of a BCG-TB vaccine, all the way to creating the first rapid blood test for TB, which is incredible, and delineating the infectious window of SARS-CoV-2 and its mode of spread in households. And by devising the first IGRA-based national screening program for latent TB in new migrants, Ajit has also helped to have England's TB burden in recent years, which is an amazing accomplishment. Ajit also supports the public's engagement with science through his role as a governor of the Science Museum Group in London. And finally, he has actively developed India's medical research ecosystem through chairing the Strategic Advisory Board of the India Alliance, which is India's preeminent medical research funding organization. Dr. Lalvani's talk today is entitled Determinants of SARS-CoV-2 Infectiousness and Transmission. Thank you very much for joining us, and please take it away.
Thank you for the introduction, Nicole, and thank you for the kind invitation to speak here today. It's a pleasure to be back at this veritable temple of public health research. I've got a lot to get through, so I will just start illustrating, if that's okay, and begin by just paying tribute to the incredible team that agglomerated around me during the pandemic. These are the scientists, but in addition to the scientists and researchers on CVA, we actually brought in about 25 different helpers, just young people who just came in, paid on an hourly basis to help us set up the studies that formed our pandemic research response in the first few months of the pandemic. There were two main cohorts who did. The first is known as Instinct, and the goal was to identify correlates of protecting immunity against infection and disease. And I won't be talking about those outcomes and results today, although many of the patients, many of the individuals in the Instinct cohort contribute to the studies I'll be presenting. What I'll be focusing more on is the second cohort, the assessment of transmission and contagiousness of COVID-19 in contacts, known as the TAC, funded by the UK's Chief Medical Officer at Speed to answer additional public health questions, piggybacking on Instinct, which had already started. Instinct was a household contact study, and so TAC came to leverage off of that household contact study to answer questions related to transmission. So this shows you the study design, sampling schedule, going into households, research nurse team, full PPE at the time, obviously pre-vaccination, 2020 and 2021. And on average, we managed to recruit contacts at a median of 3 days after symptom onset in the index case. So approximately 3 days from exposure. These contacts in the TAC had daily nose and throat swabs that they carried out themselves, stored in the fridge, and then they were couriered daily to London to the labs for analysis. But in Instinct, they also got additional sampling on days 0, 4, 7, 14, and 28, which included blood samples at all of those time points, nasal lining fluid, and also on days 0 and 7, and environmental surface swabs in the households. So we aimed really to address the following key public health knowledge gaps early in the pandemic in order to inform policy. And I think that these are potentially generalizable to future pandemics as well, because I think what I'm listing here are important questions that are best answered through household contact studies, and they're all questions, the answers to which are helpful to inform policy in the first weeks and months of managing the pandemic. And I'll take you through each of these now. And the first is identifying the earliest symptoms in newly exposed contacts to inform syndromic case definition. And I won't spend long on this, but it just to share with you as epidemiologists the power of this sort of study design, because of course household contacts are people who've just been exposed to the pathogen. At the point of enrollment, some are already PCR positive, the majority in fact, but a good number are also not yet PCR positive when they become infected during the early days of follow-up. So what this allows you to do, what we did here, where we used Instinct as a training cohort, on the left and on the right, we used a test cohort, where we were training and testing was the accuracy of various symptoms to formulate an early syndromic diagnosis. And this shows you the sort of results you can get with this kind of study design. On the x-axis is time since exposure, and on the y-axis is the proportion that become that are PCR positive. And you can see the different colored lines in the survival plots. So you have different symptoms and capture, if you like, people who are becoming infected with COVID at the earliest time. So the two left-hand graphs are PCR positive contacts who became infected, and on the right, the control, if you like. So these are exposed contacts in the household, but who remain PCR negative. And so you can see the different colors, the different colored lines. CS is canonical symptoms, and so you can see how well or unwell the canonical symptoms perform versus a new approach we developed, which we found, which was these EPs or early predictors of COVID. So symptoms in addition to the canonical symptoms. And through this kind of analysis, we concluded that actually 29% of infected contacts did not report any of the canonical symptoms, which were fever, cough, and anosmia or loss of taste. But 4 additional symptoms that we tested, sore throat, muscle aches, headache, and appetite loss, these were identified as early predictors, and we came up with a new rule that says that if you have 1 or more canonical symptoms or 2 or more early predictors, you're very likely to have COVID. And that allows you to detect people with COVID on average 2 days earlier than the canonical symptoms. So being able to diagnose, test, and then isolate a report 2 days earlier would have been decisive in controlling the pandemic. And using these additional early predictive symptoms resulted in only a modest reduction in specificity of 5.7%. And this kind of study design that could all implement daily symptom records, this enabled us to look and see, in real time, what symptoms occur, which ones associated with predicted PCR positive, and which ones are noise that are occurring in the PCR records. Towards the end of 2021, second half of 2021, this orange curve shows you that despite the early rollout of vaccination, we were facing a new wave with the Delta variant, suggesting that it was perhaps cutting through the newly vaccinated population. So at high speed, through attack, we carried out this study which demonstrated for the first time community transmission between fully vaccinated index cases and fully vaccinated contacts. And I will, without laboring the point too much here, just to point out that 23% of what we were able to do here was to slice the results both ways, because we could stratify contacts by vaccination status, but also the index cases by vaccination status. And we found that 23% of household contacts exposed to unvaccinated index cases resulted in transmission. But so too did 25% of household contacts exposed to fully vaccinated index cases, suggesting that the vaccinated index cases were similarly infectious to the unvaccinated index cases. And we found that fully 23% of household transmission events were from fully vaccinated index cases to fully vaccinated household contact. And this shows you here in the plots B. In plot B, you can see 3 graphs here. This household 1, household 2, household 3. Both the index and the contact are fully vaccinated, and yet the viral load on the y-axis, a copy number in the index cases in red, is seen here as it declines, but you can see the contacts in blue getting infected, and the diagram at the top shows you that in these households, the strain of SARS-CoV-2 was identical between index cases and contacts, so confirming household transmission quite efficiently between fully vaccinated index cases and contact pairs. This just shows you diagrammatically the importance of this finding, the relevance. The bubble indicates vaccination, and you can see that whilst vaccination means that your index case will have only mild illness and will be symptom-free, fortunately, but they remain infectious. The contacts who are vaccinated acquire infection and transmit onwards. And so this sets up chains in the community of ongoing transmission that we're now familiar with. The other thing we found in the diagonal red line shown here was that already within 3 months after the second vaccine dose, the protective effect of vaccination against infection, not against illness, but against infection, was already declining substantially. We had the opportunity to look into viral load kinetics in 133 individuals, because we had plots from almost daily or almost daily RT-PCR on these individuals. And essentially, what we found quite a few interesting findings from this, and this graph is color-coded for pre-alpha, alpha, and delta. And essentially what we found was that the growth rate predicts the peak. So the growth rate correlates strongly with the peak viral load, and it also correlates strongly with the decline phase, or it correlates inversely with the decline rate. So that the faster the growth rate of viral RNA copy number, the longer will be the decline phase, and the higher is the peak. And on average, that growth rate was 3 days. And we asked ourselves in the same study, what's the impact of vaccination on the viral load kinetics? And what we found, just shown sort of already here, is that the effect of vaccination, it didn't reduce the peak in terms of viral load peak significantly. But what it did do was shorten the decline phase by about 3 days. And so this faster appearance of infection, we believe, is what results in the faster appearance of infection that you get with vaccination. It's probably what's really helping to explain why vaccinated breakthrough infections have faster symptom resolution and less risk of developing severe illness. But we interpret this to explain also why there's no significant reduction in peak viral load, but that's probably why the vaccines were not successful at very substantially decreasing infectiousness and transmission. But to better understand actual infectiousness, this graph showing you the blue line vaccinated, the flat line unvaccinated. It's all with the y-axis being viral copy number, RNA. But we know that just being RNA PCR positive doesn't mean infectiousness. The best biomarker for infectiousness is viral culture. So plaque-forming units, quantified units, PFUs. So we wanted to try to define what is this actual window of infectiousness that Stephen Kister was talking about so eloquently just in the last hour. And we set out to do this empirically in these cohorts. And this is how. This just depicts for you the assay that's carried out in continuum level 3, plaque-forming units, virus growing on cultures of mammalian cells, in vitro cognitive cells. This shows you the cohort. Total number at the top was 738 for this study. But we wanted to define the window of infectiousness. We needed to define the left-hand edge and the right-hand edge. So onset of infectiousness and end of infectiousness. So that meant we needed a sub-cohort from this where we actually captured the growth phase of the virus. And ideally, where we also, in most of the 57, where we captured the very onset. In other words, incident cases who were initially PCR negative, but became PCR positive in the first few days after enrollment. So that's what comprised the Cohort 57, on which we then did these very labor-intensive platform unit assays to quantify the amount of infectious virus, and we correlated that with symptom onset. And in these representative graphs from sample 57, the dashed red line in each case represents symptom onset. The orange lines show you a viral load copy number, RNA, and then the purple lines show you the platform units. And the obvious take-home messages here are that the platform units, the infectious virus load, is 2 to 3 logs lower than the viral copy number. Secondly, that this purple graph, the infectiousness, takes off a bit later, a day or 2 days later, than the RNA is first detectable by PCR. Thirdly, when it does take off, it gets to peak very fast, and then it declines also faster than RNA copy number. At the very top, the boxes you can see are the corresponding results from lateral flow assays, because we using the study to correlate lateral flow test results with actual infectiousness. So perhaps a couple of things to bring out, though, that as you can see here, the yellow coloring shows you where the yellow is coloring to the left of that vertical dashed red line, which is onset of infectious. And as you can see here, quite a number of individuals have a PCR positive detectable RNA, but they don't have detectable infectious virus until the onset or after the onset of symptoms. And overall, we found that actually only 20% of our individuals were shedding infectious virus before the onset of symptoms, lower than what was estimated from the previous modeling studies. So this is asking whether we can infer the effects of protective immunity from viral load kinetics. Now, on the left is a table showing you the, if you look at the row, it's the row just here. So the penultimate row of the table, growth phase, the growth phase duration. So you can see here for RNA is 3.6 days, but for infectious virus is 1.6 days. So that growth phase from undetectable infectious virus to peak infectious virus is 1.5 days. And after that, basically the host pathogen equilibrium pivots away from viral growth to viral control in less than 2 days. And to me, this invokes a crucial role for innate mucosal immunity that turns the balance, turns the tables on the pathogen at that point. So I see that as a crucial control point mediated almost certainly by very early innate mucosal responses. I say mucosal because if it's that quick, it's unlikely to require systemic responses to turn it around fast enough. After all, these are viral loads or infectious viral loads in the respiratory tract. On the right, sorry, it's a bit of overlap here, but the x-axis days since first PCR done. That's the x-axis of the right-hand graph. And as you can see on the left is the ratio of RNA copy number to platform units. So in other words, it's the amount of RNA produced divided by actual infectious virions. As you can see, this is increasing substantially over time. Note how the y-axis is drawn. Okay? The y-axis is drawn that way because it's showing you that the viability of virus is declining over time. So you need, you essentially need many more copy numbers to produce one infectious viral virion over the 14 days course of the infection. And what that suggests to me is that during the course of infection, adaptive immunity now is kicked in and is making the virus less viable. And so, as Steve Kissler was saying earlier, if that is your first name, Steve. Steve was saying earlier, because I'm just familiar more with the papers than with yourself. So it was Kitchener. Yeah. So, this, part of what you were trying to point at with the elegant modeling that showed us was it's shown empirically actually here, because of course what the study allowed us to do is to do Kaplan-Meier survival plots, look at the probability of continued presence of infectious virus at any given day after symptom onset. And this shows you those results. The black line just shows you that survival probability over time. And you can see by 10 days on the x-axis there's basically zero probability of presence of infectious virus across this population, remember, of only 57 people. So it's based on a small number of individuals. So the confidence intervals are wide. But if you were to apply a 7-day rule shown in red, and release people after 7 days of isolation, you can see reading off the y-axis, you'd be about 30% of the people you release would still be infectious. And if you use the 5-day rule, the blue dashed line, and read off the y-axis, you can see that 2/3 of the people you release would still be infectious. That's quite alarming. But of course, the amount of infectiousness at that point is less than it is at the onset of infection, because as you saw from the empiric data that occurs, it's declining, the infectiousness declining over time. We identified at the start a lack of robust studies really evaluating the accuracy of lateral flow tests for diagnosis or for isolation in COVID, and what really should be their role and how should they be used. So we applied this test, the NOVA test, to these 57 individuals, and essentially what we found was that prior to the peak, at the peak viral load, sensitivity was only 67%. Specificity was good, but that's a very low sensitivity, cautioning against the use of lateral flow for early diagnosis of COVID. But we found that after peak viral load, the sensitivity was a lot higher, 92%. So this actually led us to develop a rule that actually then influenced policy within 2 weeks of us analyzing these data into policy in the UK, which was to allow people out of self-isolation earlier if they got 2 consecutive negative lateral flow test results. So I said, if you like, shortening the isolation period and doing ultimately what's rational and evidence-based, which is tailoring it to the duration of the test. This one pictographic or infographic summarizes basically everything I've just told you, so I won't go on it for now. But the take-home message visually is light blue, it's the PCR detected mRNA copy number, and in pink, the infectious virus. Now, the median infectious window was 5 days long. And Stephen mentioned to us earlier that estimates have been 5 or 6 days, so we measured it in actually 5 days. But in the middle there, middle of these 3 graphs, is a normal sort of individual, if you like, with a 5-day window. And on the left and the right are 2 individuals that had notably prominent travel. And if you look at their purple lines, the infectious virus, you can see that even out to the last day of follow-up, they were still positive. This was actually quite striking. And it turned out they were both diabetic. They were the only 2 diabetics in our whole cohort of 57. So quite a remarkable coincidence. And we sequenced their genomes to see whether what was happening during this prolonged period of infectious virus shedding. And we found, interestingly, in both of them, they developed TMVO mutations during the course of their infection. And one of these, the one shown here, is actually a previously defined immune escape variant. And you can see the yellow, the viral copy number, and in the green, the plaque-forming units. And you can see at the end that sort of rise in plaque-forming units, suggesting a sort of rebound as the mutation appears, shown down here in the box there. The mutation appears, and then the infectious viral load rebounds upward, suggesting its actual in vivo immune escape. So we asked ourselves a question. These data are generated by Jakob Nanaby, the physicist and mathematical modeler. We aim to understand with Jakob what is the utility of viral load dynamics? And we wanted to understand within host viral dynamics and how it relates to immune response, symptoms, and but particularly also to infectiousness and onward transmission. And as I mentioned to you, growth rate, viral load growth rate correlates positively with peak viral load and negatively with the decline rate. And you know, we wanted to see what information can we glean viral load kinetics regarding infectiousness and transmission. In reality, we practically go and do infectious viral load measurements, performing assays in the field, in an outbreak setting. And also, you couldn't really do it in large-scale epi studies either, nor would you ever normally be able to capture the onset of infectiousness, the left-hand window, as I described it earlier. So we tried to figure out, were there measures more easily available would be used to infer infectiousness and potential transmission. And so, because viral load decline rate here correlates a negative growth rate, we focused on that to see what the viral rate performs. And you can see here in black, you know, RNA copy number, the curves you've seen, and in red, infectious load. And you can see a given reading from the PCR. Now, that one reading would represent a number of different viral load trajectories. You don't know which. But if you have a second reading, you can actually then infer what is the viral load trajectory of that individual sample. And we therefore thought that decline rate and decline time may therefore provide information about viral load kinetics earlier in the course of infection, like leading backwards, as it were. And our hypothesis was that upper respiratory tract or URT RNA decline time correlates with AUC, area under the curve, and therefore potentially with infections. So using those two data points that compute decline rate and decline time, and then work backwards. So that's what we did. We did it in 47 of the cases described previously, where we had the relevant data points, and this is what we found, that the RNA decline time with Bayesian modeling actually correlates very well with the area under the curve of RNA copies. And when we did the same thing for plaque-forming units for infectious virus, we found that decline time of infectious virus correlated well with area under the curve of plaque-forming units. So potentially correlating with infectiousness. But would that actually correlate with transmission? That was the next question. So to do that, we in a proportion of those 47 individuals I showed you now, we also had the corresponding contacts. And so we could do that. And the sample size of this final subcohort here is 38 index cases and 69 contacts. And in here you can see that as the decline time increases, the higher the decline time in that index case, then the higher the secondary attack rate amongst that index case's contacts. So in other words, the decline time correlates positively with transmission. We wondered if this might be a more generalizable phenomenon to other respiratory viral infections. So together with our colleague and collaborator Ben Cowan in Hong Kong, we studied his data set of an influenza community study he carried out in Hong Kong. And actually here you can see, interestingly, that SARS-CoV-2 and influenza index cases display similar viral decline rates, as you can see at the distribution frequencies, really remarkably similar for both viruses. So then we asked, does the decline time, viral load decline time, we couldn't do infectious PFUs because Ben didn't have those data, but does the viral load decline time correlate with the area in the curve of viral load in flu? And the answer is it does. So we're hopeful that this is a sort of generalizable phenomenon we've uncovered. And that also applies to transmission in Ben's community study, because as you can see here, the longer the decline time, the higher the secondary attack rate amongst the contacts of those index cases, very similar to what we saw. So that's conclusion, but I think it's I don't need to repeat that. That's pretty clear from what I've said. And so to the final part of the talk is we took the opportunity of these household studies to try to figure out what are the risk factors infected for SARS-CoV-2 or outcome transmission. And in this study just published last Friday in Lancet Microbe, we aim to the hypothesis is basically shown here. And to test that hypothesis, right? And that is, I think it's important to say that that's not been shown today. So when we say transmission of airborne or transmissions through hands and surfaces, there's no empiric evidence actually showing that, or there is a lot of modeling showing that both are plausible. There's epidemiological evidence showing that in certain settings that requires airborne transmission must be the route because there's no contact and it's long distance. And then there's also microbiological studies detecting the virus basically everywhere, in the air, on surfaces, and so on and so forth. But there's no study correlating the presence of virus on any surface or air or environment with actual transmission. So that's what we set out to do here. To do that, you have to maximally capture contacts. You need contacts that are naive, so you need to do it at the start of the pandemic, and you need to maximally detect them. You have to make sure you're capturing every case in the household. But our study design, as you'll appreciate, does that. We follow the last serially with PCR, and in a subset we were able to do a baseline and serial serology. So we could really be sure picking up everyone, either by PCR or serology or both. We could be also sure who isn't infected as well as who isn't. So this just shows you, 400 contacts came from attack, 200 from instinct. This shows you the sampling schedule, which I've shown you earlier. But just note here that at day 1 and day 7, we also did hand swabs, and we swabbed frequently touched surfaces in the household. Right, so we did cooking taps, fridge handles, kettle handles, that kind of thing. And you can see the results in terms of correlation with proximity, duration of exposure. You can see here the relationship, because we recorded the relationship of each contact with the index case. If they were a partner or a parent-child relationship, or sleeping in the same bedroom, they were much more likely to be infected than if they were parent to child or sibling or without shared bedroom, and then less still if they were housemates, but less close relationship. So you can see the correlation with relationship score exposure within the households. You can also see that whereas for preempt for the secondary attack rate was 28%, for alpha it was 52%, really striking. This shows you that in those individuals where from the index case and the contact we had sufficient material, RNA, to do whole genome sequencing. That was the case for 25 in the household. In every single household, the two strains were indistinguishable. So this was actual transmission, household transmission between index cases and their contacts. So what were the determinants then of transmission? And you can see here that the primary case, index case, for respiratory tract viral load, URP viral load, did not correlate with transmission, right? Which itself was interesting. Other larger studies have shown that it does correlate, it didn't. But what we did find intriguingly was that the higher the upper respiratory tract viral load in the index case, the more likely they were to have contaminated their hands, to have a positive hand swab. That was a significant association. And in turn, we found that the presence of SARS-CoV-2 on the primary case's hands was correlated with the detection of the virus on their respective contacts. So here we're correlating the upper respiratory tract viral load with the primary case's own hand with the contact's hands, then in turn being more likely to be positive for virus. And you can see here at the top is the PCR status, negative or positive, of the contacts themselves. And going down the rows, you can see the different factors. The primary cases hand swab was almost significantly 1.7 increased risk of the contact being infected. If the contact's hand was positive, their own hand, they were twice as likely to be infected as if their hand was not positive. And if one of the environmental surface swabs was positive, they were 1.7 times more likely to be infected, and that was not the case. So these were the factors strongly associated with the risk of infection in these susceptible contacts.
We have about 1 minute left.
Okay, in terms of directionality, we have prevalent cases, but we also have incident cases, which are shown here in red. And in the incident cases, we had results from the household swabs and the hand swabs at T0 before they became upper respiratory tract PCR positive, before they became infected. And what we found was in 6 such individuals, they had either positive hand swabs or positive household surface swabs before they became infected, suggesting directionality of transmission from hand or surface into the contact to cause them to be infected. And this is the last data slide, and this is interesting because it shows you the one explanation for some of these findings might be, well, the PCR, the households with the PCR positive contacts, they're the most recently infected people. They will just be retrograde contaminating the environment around. But the p-values at the top of the slide show you that whether the whether the contacts in the household were PCR positive or negative, whether they got infected or not, the viral load quantity contamination and the corresponding hand swabs and surface swabs was non-different. So it probably wasn't retrograde contamination, so that you just got more virus detectable because there's a PCR positive contact there. Because the y-axis of this slide is actually the copy number virus on the hand swabs and the surface swabs. Lastly, what this shows you, if you look at the key at the bottom, the black dots, baseline seropositive, and the empty circles are baseline seronegative. And one question that we had actually from a reviewer was, what is going on in people who, for example, where you've got a positive hand swab, right? But they are PCR negative. And so they got a positive hand swab with this sort of level of copy number, and yet they remain PCR negative. What's going on there? And the same here. Positive hand swabs with these sort of viral loads. So these are surface swabs, and yet the contact is negative in the upper respiratory tract. Turns out the vast majority of people of that type, baseline seropositive. So they were immune, whether through prior infection or vaccination. This speaks of mostly vaccination. So this suggests that you have the virus lurking around where the people are not getting infected despite virus in the environment. It's because in almost every case, it actually is a baseline seropositive. This just shows you finally how we see the pathway, and it shows you the impact of being seropositive that protects you from the virus in the environment. And I'd just like to finish by thanking everyone here, and also to mention how much we've appreciated and been stimulated by your own studies coming out of the CCDD over this last 2-3 years, and it's been a very enjoyable and intellectually stimulating process of cross-fertilizing each other's study. Thank you.
Thank you very much for this terrific talk, Dr. Lalvani. I think we have time probably for 2 questions max. So we'll start with anybody in the room who has questions.
Thank you for the great talk. I was wondering if you also sampled air samples for the last study, and whether the contaminated surfaces would more correlate with airborne samples as well. Yeah.
It's a great question, and we started doing that with the sample Coriolanus, but we only had one device, so we could, and each time you use it, you have to take it back to the lab to process the filter paper in it. So what it meant was we could only sample a very small proportion of hospitals. So the quantity of data, it just wasn't systematic enough to be able to properly include it in the paper. Where we sampled was not next to the patient's bed in the house, because we figured what would probably be there. So what we did is we did with the hand swabs, we sampled communal areas. And in the dozen or so households where we did it, with infectious index cases, we didn't find the virus once. In these communal areas, which is really good. But we couldn't put it in the paper because it was just very, preliminary sort of data. My colleagues with the controlled human infection challenge model in Imperial are about to publish a paper also in Lancet Micro showing that you do get air contamination after you become infectious after challenge, but that 80% of what was detected in the air came from 2 individuals. So the minority of individuals emit into the air, and when they do, they emit a lot, and they may be super spreaders. But they also found a lot of environmental contamination in their experimental challenge study, as we found in the host.
Thank you for the great talk and summary of incredible work and just an amazing setup for doing all this work. I'm curious about now the policy implications for some of this, and what do you think we should be doing in terms of encouraging people to isolate after positive tests from, now that we are getting moving into a different phase as well in the pandemic. Flu, which you showed might have a very similar kind of pattern. We don't ask people to isolate. Should we be doing the same thing now for COVID? Or if not, what kinds of guidelines should we propose?
I mean, the latest data from the Research Surveillance Centre in the UK, at the Royal College of GPs, so the NHS system, and it covers actually, almost half of the UK population now. It shows that COVID, SARS-CoV-2 isolates are largely associated now with coryzal symptoms, common cold symptoms, rather than influenza-like illness. And so I do think that whether it's the virus or the host immunity, but it's obviously both at the same time, it's basically becoming a common cold. So I would say that isolation in the vast majority of instances is not required. I must say, if I were thinking of an elderly, vulnerable person, say my mother or father, I would probably still self-isolate, but wouldn't say that's particularly evidence-based because they're quadruple or quintuple vaccinated. What's their real risk? It's going to be extremely low. So I think by and large, isolation doesn't make sense anymore, but in certain circumstances, it may do.
Any other questions from the gallery?
I think Jonathan's question one step further, which you didn't ask me. I was hoping you wouldn't ask me about vaccination, but it isn't worth maybe asking. A very striking slide that Jamie Lopez-Bernal, my colleague at UKHSA, shows is that the number needed to treat, or number needed to vaccinate NMV to prevent hospitalization with zoster vaccine to prevent hospitalization from shingles is 60. And the corresponding number needed to vaccinate to prevent hospitalization with COVID vaccine was 800. So I'm glad you didn't ask me about that. I think it's a very, how do you decide this? One of the things that what we were discussing in the lift with, I forget the name of your friend who's going to Moderna, exactly about the role of vaccination going forward too. So interesting numbers.
Wonderful. Well, on behalf of the Center for Communicable Disease Dynamics and the Harvard Change Chance to Public Health, I'd like to thank Dr. Lalvani